Hello, this is Chris Dugan, and today I'm joined with Mesut Uzman, who is the CEO of Fermi America Nuclear. And we're very privileged to have such a genius in his space with us today to kind of go through many of the misnomers and a lot of the misunderstandings with nuclear. It's such a powerful carbon free electricity provider. And today we're going to learn more about all about this and more about his project, if you will, Masood.
Hi, Chris. Thank you for having me joining this podcast. I'm very happy to be here. My name is Mesut Uzman. I'm an American citizen, originally from Turkey. I educated at the Ohio State University, where I earned my master's degree in electrical engineering. Then I spent 28 years in the nuclear industry. And after involving in many nuclear upgrade projects in the United States and in Europe, built power plants in China and in United Arab Emirates. But now I'm home. This is home for me now, West Texas, and I couldn't be more excited about what we are going to build here. My career started at Westinghouse, at the company that invented civilian nuclear power. I spent 14 years there, became one of their youngest directors in the company's recent history, and led the development of advanced instrumentation and control systems used in nuclear power plants around the world. I then spent time overseeing 8 nuclear power stations being built simultaneously in China, 8 of them, all at once. And that experience in managing complexity at that scale is exactly what prepared me for what we are doing at Fermi America. And most recently, I spent over a decade in the United Arab Emirates, helping build Baraka, a 4-reactor nuclear energy program totaling more than $26 billion. We brought all 4 units to commercial operation. We made history together with the Emiratis. And now I brought everything I love on 4 continents back here to the Texas Panhandle, because I believe America is ready to lead the world in nuclear energy again. And Fermi America is how we will do it.
Excellent. Well, thank you very much for that introduction. And it's literally amazing, obviously, given your experience and the fact that these silent electricity mega plants are functioning as we speak around the world with little or no issues whatsoever. And so, again, to have your ability to bring that back to the United States, which we've been missing for so many years, this opportunity. And as we had spoken just briefly before, if there was ever a time where I believe the United States is ready to get back into the nuclear game at scale, it's this time, and with your, obviously, your expertise. And so can I, with that, if I may, I would like to speak to, if you can give the benefits, other than what most people know about the carbon footprint being zero, and a few other amazing things like the scale of gigawatts that come out of a nuclear plant. But can you speak to why nuclear is the better option long term over other power, electricity power providers?
Sure, Chris. Just don't get me wrong. I'm all about other renewable sources as well. But we consider nuclear as the base load option. Just let me put it in this way. Think of electricity like a restaurant, right? Solar and wind are the wonderful seasonal specials. They're delicious when available, but you can't build a menu around them alone, because sometimes the sun isn't shining and the wind isn't blowing. You still need to eat dinner. And nuclear is the kitchen that never closes. So Here are the hard numbers, right? The nuclear plants run at over 92% capacity factor, meaning they are producing power more than 9 days out of every 10. Now, in comparison, solar averages around 25%. Wind is about 35%. That means for every megawatt of nuclear you build, you would need 4 to 5 times the nameplate capacity in solar or wind to match the output. And of course, you need to get additional expensive batteries to store the energy with those solutions. But here's one of the other part that surprises most people. Nuclear is one of the cleanest energy sources ever created, as you just mentioned. And the United Nations Intergovernmental Panel on Climate Change, they are considered the gold standard for climate science. They measured the full life cycle of carbon emission of every energy source. So this is from the production to the operation over the lifetime of the energy generating asset. The result, coal emits around 820 grams of carbon dioxide per kilowatt hour. Natural gas is about 490. Solar, 48. And nuclear, well, nuclear is only 12 grams. It's very comparable to wind, which is 11. So nuclear is cleaner than solar, that most people don't know that. Nuclear is also reliable in a way that goes beyond just capacity factor. It is the only carbon-free power, as you mentioned, source that can provide true baseload power, on demand, 24/7, year-round, regardless of weather, not intermittent, not seasonal, always on. And nuclear is uniquely energy dense, right? One uranium fuel pellet, about the size of a pencil eraser, contains the same energy as 149 gallons of oil, 17,000 cubic feet of natural gas, or 1,700 pounds of coal. That's not a metaphor, by the way, that's just physics. So this is why, and this is also important, I want to mention this. This is why Fermi America's co-founder, Toby Nagelbauer, says a superpower has nuclear-powered aircraft carriers. A superpower has nuclear-powered submarines. And now a superpower needs nuclear-powered AI. The same principle, concentrated, reliable, independent power for our AI.
Excellent, excellent. Appreciate that. And to get a little bit scientific here and kind of tap your gray matter, so to speak. You mentioned baseload power, which I think is really important for viewers to understand. Can you speak to, and it kind of goes into the question I was going to ask you about behind the meter power. So can you start with explaining a little bit about the importance of baseload power and having something at scale of this size as baseload power because of the issues that could evolve from frequency deviation due to heavy loads on a typical small megawatt size system? Can you explain that, please?
Correct. So let's just put it this way. In the nuclear industry, we are also very green, and then we are looking for renewable sources as much as possible to be used. However, when it comes to certain critical loads, what are they? Like our hospitals, our roads, our factories, our schools, right? So those need, and now our AI need, a reliable, always on power. So that is the bare minimum that we cannot take a cut of power to these utilities, these facilities. So that is the definition of the base load. So then we have a base load to cover those in a bulk amount, very reliable power source. Then for everything else, we can then use other sources of energies like the solar, like the wind. And if we lose power intermittent every once in a while, it's not a big deal, right? So that is the difference between the baseload power and then this other sources which can provide us on and off power as the demand goes up and as the demand goes down.
Okay, appreciate that. Now, just so the viewers understand, there's there's a lot of, I believe, a kind of conjecture out there, a lot of conversation, but a lot of misinformation about those generating power, but they're pulling from like a base load system, or they're pulling from an established power source to go ahead and fuel these AI data centers. Can you explain the behind the meter concept and how that's not the case? It's just the absolute opposite. This will not negatively affect consumers of electricity because of your generation.
Correct. And that's a valid concern by the public that obviously if there's a very large demand on the general grid for electricity, the general public should not be, consumers should not be competing against world's largest, richest companies to get this power because we can predict what will happen at the end. So our solution is therefore totally different. So that's the behind the meter idea is coming from. So let's put it this way. Most people get their electricity through the utility grid. Power flows from a distant plant through hundreds of miles of transmission lines to their home. The utility meter on your wall measures that, and that's in front of the meter. Or behind the meter project, it means that we generate and consume our own electricity privately without going through the public utility at all. Think of it like digging your own well instead of connecting to city water. You own the source, the pipes, and the pump. That's all you. And then you are not using any of the city water sharing with anyone else. At Project Matador, we're building 11 gigawatts of generation, including nuclear, natural gas, solar, and obviously battery storage systems. They all integrate into a private grid. The power goes directly to data centers and AI infrastructure on our campus. We are also interconnected with the utility grid as a backup option, but that is just for starting up initially, because we are all black site. That if you understand the term, that we don't have any power generation at the beginning, so we need some power to start the construction, but it is very limited. But our campus is designed to be self-sufficient. So this matters because next generation AI data centers need power reliably in the order of 99 point multiple nines percentages. This is as close as never going down as you get, right? So this is the technical term for that. They also need massive amounts of it, and no utility in America today is set up to deliver 11 gigawatts to a single private campus. So we built our own grid. It is the largest behind-the-meter private energy grid in America history. And we are doing it so that consumers will not be impacted, regular electricity consumers will not be impacted by our project when we provide this power to the AI data centers or the race in AI. And we need to win this race, so we need this power to get to them. But we don't want to do this hurting the consumers. So this is our creative way of doing it.
Excellent. Well, thank you for being able to explain that, because I think that's such a critical distinction for those to understand that AI in this capacity that you're generating the power for is not impacting them in any way as far as their rates or as far as any power usage on the grid that they're currently involved in. And as you mentioned, which is so important, to try to compete against hyperscalers like Google and these others, where they have endless resources of cash, so to speak. Yeah, this is not an impact. And one thing I'd like to, if I could stay on the science aspect and kind of tap your vast knowledge. You mentioned that you worked for Westinghouse, which of course is the standard. The AP1000 is the standard for nuclear reactors, nuclear power plants in the United States and actually in the world. And so, can you speak to, there's a big push currently, and to my knowledge, we still haven't seen one actually functioning. But the AP1000 versus the SMR, the small modular reactors, can you speak to the advantages of the AP1000 and kind of set the stage of how that looks?
Of course. Yeah, I mean, yes, in the news these days, we all keep hearing the SMRs and SMR technologies. There is a fundamental difference that need to be explained. So SMR, by definition, smaller reactor, typically under 300 megawatts, and designed to be factory built and shipped to site. The idea is elegant, and for the right application, such as a remote community, a small industrial complex, replacing a retired coal plant on a small grid, SMRs make a lot of sense. Okay? So that there is no argument about that. And also, there are now SMRs going to generation 4, which are more efficient and working at the higher temperature. And that high temperature is also not for electricity generation, but then it has some advantages for chemical plants, some of the petrochemical industries, and even for hydrogen generation as the byproducts. So there is a specific use for the SMRs. But let me tell you why SMRs are fundamentally wrong solution for what we are doing at the Project Matador. We are not building for a small grid. Let me put this in perspective, right? Our site is Amarillo is about half the size of Manhattan Island. But the power we are going to produce is equivalent to the entire state of New York's consumption. When our first AP1000 units comes online at 1100 megawatt, that single unit will produce more electricity than the entire state of Alaska uses at peak demand. So Alaska's railbed grid, which serves most of the state, peaks at around 750 megawatts. One of our 4 units exceeds that. When Unit 2 comes online, we will be generating more than the entire state of Hawaii. Right? So now compare that to the SMRs. Westinghouse makes a product called AP300. Other than AP1000, they also have AP300, which is a miniaturized version of our AP1000. It's a brilliant piece of engineering. It uses approximately half of the construction materials of an AP1000, but it produces 330 megawatts, less than a third of the AP1000's output. So when per kilowatt hour of electricity you produce, the AP1000 ends up significantly more expensive, roughly double the AP1000 cost per kilowatt. To match one of our AP1000 units, you would need 3 to 4 AP300 units. Even if they are half the cost, quarter the power, so double expensive. And because they all need their licensing on construction side, on commissioning, that doesn't make sense at our scale.
Right.
But again, there are applications where AP300 makes perfect sense. The AP1000, by contrast, is a proven design. 2 AP1000 units are already running in Vogel in Georgia, the first new nuclear built in America in 30 years. Watts Bar Unit 2 was a plant completion, so I'm not really considering that as a new build. And our combined operating license references AP1000 design certification. Now it's going to reference to Rev 20, which incorporates every lesson learned from Vogel and from our 4 units also in China. Westinghouse built 4 units in China. We are not the first of a kind. We are a proven copy. And in the nuclear industry, being the first of a kind costs you years and billions. And we already paid that learning curve as Westinghouse, as nation. So now it is time to get the benefit of the nth of a kind for reliable power generation at a meaningful cost.
Right. Excellent. So, if I may, just to kind of set the stage and with your vast experience, particularly in China, so to give context to what's going on currently, uh, China is roughly rolling out, it seems like a reactor a month currently.
Yeah,
It seems to be on that scale. Yeah,
Chris, yeah,
go ahead.
that is correct. Right now, in fact, there are 14 AP1000 reactors under construction in China. So the original, this was a landmark contract between Westinghouse Consortium and the China State National uh, years ago for the initial 4 AP1000 that required also a technology transfer. So now Chinese are calling their AP1000 CAP1000, and they are building them in a crazy pace. So the first CAP1000 is already online, and then the second one is all coming, and then throughout to like next 10 years, there will be 14 of them coming online. It is the same design we are building. So that explains that the global demand is why the supply chain is under pressure. And it also tells you something important. The world's largest economies are betting heavily on the AP1000 technology. China obviously isn't building those 40 reactors to be nice to their citizens' electricity bill. And they're building them to win the AI race. And so are we also doing the same thing.
Right. Just a question. I'm kind of intrigued. So we both, have traveled to China. We both are familiar with China. Um, Shenzhen is their Silicon Valley. They have multiple reactors that are currently in operation and multiple that they're building. Do you see in the future Amarillo becoming maybe a secondary, just because of co-location, access to power, low latency, that kind of thing? Do you see Amarillo kind of growing in the tech hub scenario?
Well, just let's put it this way, right? So this campus and the that we are creating for 11 gigawatt in a small area for operation, it is going to be one of the most high-tech grid operation ever in the world, not in the US, in the world, right? If you look at the US grid, which is older than 100 years, it is not suitable for this modern load, the spikes and the AI load profiles and everything. So what we are putting together is a like state-of-the-art grid. It's going to be controlled by state-of-the-art equipment. We are implementing this centralized command and control facility to remotely control, monitor every asset and our grid in a central location. So our plans include providing uh, training simulators to the local colleges to make sure that we have a workforce coming and working, running our site, this state-of-the-art site. And there will be so many job opportunities for that. And I'm not talking about just for a few years, right? Our AP1000s technically are there until year 2100, right? So then this is generations of power. In the future, things will change, and I'm expecting that Amarillo with Project Matador attracting all the high-tech companies to the area for work will also be an epicenter for AI-based development. So in the next 10 years, like I'm expecting significant changes in construction industry and all other like manufacturing industry, and they all gonna be AI driven, and Amorla will be the epicenter. So then you're right, your analogy that it could be the next Silicon Valley for the AI. And you understand that also all the companies are attracted to come to Texas now. And then so in West Texas, technology companies are also growing very healthy way and so employing so many people.
Excellent. And Masood, if I may put in a shameless plug for Mesa Lands College here, we would definitely, if you could put us at the top of the list for a training simulator, we'd appreciate that.
Absolutely, absolutely, Chris.
Yes, and again, I just want to thank you very much for spending some of your time. We know that you're extremely busy getting everything in place, and obviously overseeing all these operations that you currently have going. Is there anything you'd like to leave us with? And with the caveat saying that we can have you back at a future time to follow up on some of the great things that are being undertaken.
All right. Well, thank you, Chris. I really enjoy. And then, yes, I would like to continue with this dialogue because there is this misconceptions, as you provided at the beginning of this talk, in the general public. And we need to just explain because people are afraid of what they don't know. Once they understand, then that fear is obviously like addressed. And all I can say that like the AP1000s are very reliable, but also very safe. That AP stands for Advanced Passive. So these are by far the safest reactors available in the world right now. And we can talk about this safety features and how AP1000 is different from the other reactors, maybe in the next podcast.
That would be wonderful. I appreciate it. And again, Masood, thank you very much for your time, and we look forward to speaking with you again.
Thank you, Chris.
Thank you, sir.